Hello everyone, thanks for joining today. My name is Les, Sales Manager at Listen. I'm joined with Sales Application Engineer Anastasia. I'd like to welcome you to today's seminar on loudspeaker testing basics. We would also like to extend a thank you to S&V Sanford for their help in organizing this presentation. Without further delay, let's begin the presentation on loudspeaker testing basics. Building a good performing loudspeaker can be complex because there are a lot of moving parts. Of course, there are many loudspeaker designs, but we'll look at a typical design, including the individual parts. On the left is a cutout of a loudspeaker, and on the right, a flat representation. The loudspeaker motor consists of the pole piece, top plate, and the magnet. The magnet creates a field that attracts or repels electrical charges. Without it, nothing happens. The red wire is the voice coil. The voice coil moves up and down when AC voltage is applied in the magnetic field, creating sound pressure. The diaphragm or cone is attached to the voice coil and moves to create sound waves. Ideally, it would be damped and non-resonant, but of course there are resonances. This yellow corrugated piece is the spider. The spider centers the voice coil and cone for optimal performance. It can also act as a max output. It is sort of a spring. If you try to overload the speaker, the spider will pull back. The surround terminates the cone to the basket and helps stabilize the vibrations. It also helps keep sound from the back of the cone from leaking out the side. The dust cap keeps debris from falling into the magnetic gap. Debris might include dirt, glue chips, magnetic chips, etc. Let's look at how a loudspeaker works. For this, we'll look at an early lesson in physics called the left-hand rule. That is, the magnetic field times the current creates a force. Looking at this cutaway of the magnetic motor, we have the voice coil going around the pole piece of the motor, and as we run alternating current across the voice coil, we create a force. Per the left-hand rule, the current is coming in and out of the screen, the magnetic field is going perpendicular to that, and the force moves up and down. Distortion can often be pinpointed to the magnetic motor and how well it's designed. There are a lot of trade-offs you can make to try and optimize it. So lastly, most loudspeakers are passive transducer. You must apply voltage to get output. Without input, there is no output. Let's look at a loudspeaker test setup diagram. This is an example of a basic loudspeaker test using SoundCheck. You need several things. A signal generator, in this case SoundCheck with an audio interface, typically into a power amplifier because the speaker is low impedance. If measuring impedance, we'll add an impedance box and measure the voltage across the sense resistor. We perform this impedance measurement using Ohm's law. SoundCheck calculates AC impedance versus frequency in ohms. You'll see this in Anastasia's demo. Impedance changes with frequency. Next, we measure sound pressure level, or SPL, for a given voltage, typically using some type of sweep, although we can also measure this with complex signals like speech or music. We play the test signal and measure the SPL with a calibrated reference mic with a known sensitivity. We measure the absolute SPL, typically in the range of 50 to 110 dB SPL, depending on the mic position. Also, measurement microphones are low sensitivity, so we run the mic into some type of microphone power supply to increase the gain. In short, SoundCheck will generate an AC voltage to the amplifier and record input voltage from the reference microphone and across the impedance box sense resistor, then analyze the results. It can do this simultaneously, which makes the test very fast, critical, for example, on a production line. Anastasia will demonstrate this later in the presentation using Listen's Amp Connect ISC, which consolidates these individual hardware components into a single convenient all-in-one test interface. Next, let's look at a couple of test environments. First, R&D. This could be a longer conversation, but in general, if we're testing just the driver, not a system or speaker in an enclosure, The standard is to use what's called an infinite IEC baffle. Whether we are measuring in an anechoic chamber or using SoundCheck's simulated free field measurement, we only want to measure the driver. The reason we use an infinite baffle, which obviously is not infinite, is to minimize sound waves from the back of the speaker, canceling sound waves at the front of the speaker. The bigger the baffle, the lower we can measure in frequency. With an IEC infinite baffle, this works to about 100 Hz, which wouldn't be sufficient for measuring very low frequency drivers, for example, one used in a subwoofer. The anechoic chamber has foam wedges that absorb sounds and reflections. The standard is to measure 1 meter from the speaker, although this could vary depending on the size of the driver. Lastly, the standard is typically representing the speaker's SPL at 1 watt per meter. In a QC or production line test environment, it's really not practical to go in and out of an anechoic chamber. They are big, they are expensive, and it takes a lot of time to go in and out. In this environment, we make a compromise and use a QC test box. A well-sealed test box isolates the measurement from background factory noise. Because of its size, it's far from anechoic, but it has foam wedges like an anechoic chamber to absorb reflections. The measurement microphone is placed much closer to the loudspeaker versus the 1 meter standard. This will not only minimize reflections, but it will optimize the signal to noise, which is critical in distortion measurements like rub and buzz. However, there is a trade-off. If the mic is too close to the loudspeaker, we may not be measuring high frequencies accurately because we're too close to one part of the speaker. Also, positioning is critical for repeatability. If you move the mic just a little, you can get a big change in the high frequencies as opposed to that 1 meter standard. Next, let's take a look at a few critical loudspeaker measurements. Anastasia will review these in more detail later in the presentation. First and most common, which everyone is familiar with, is frequency response. In short, if we input a frequency at a certain amplitude, a perfectly linear loudspeaker, which doesn't exist, would output a perfectly flat curve. In general, you want to minimize peaks and dips in the response. Sensitivity is a critical measurement as it will tell us a lot about our electronics. For example, if a more powerful amplifier is required. It's also important for trying to match drivers. For example, the left and right driver used in a headphone. Obviously, we want good balance on both sides. Sensitivity is measured as output over input. That is, in a linear driver, if we send more input, we get more output. Phase and polarity are related, but for the purposes of this presentation, we'll focus on polarity, which could hint at potential wiring issues. In short, a positive input causes a loudspeaker to move out. If you wire 2 speakers out of phase, you'll lose a lot of the low frequency output. With impedance, you generally want a smooth curve with 1 resonance in the low frequency. There are many types of distortion, but for the purposes of this seminar, we'll focus on THD and rub and buzz, a special kind of harmonic distortion. In short, 1 frequency in results in multiple frequencies out. The main difference between them is THD is typically low-order harmonic distortion, whereas rub and buzz is higher-order harmonic distortion. Let's look at how to measure a defect. We have a list of potential problems that can occur during manufacturing on the left. First, we could have a poorly magnetized magnet. We want to saturate the magnet for the most strength. We could have inconsistent materials. For example, if your contract manufacturer substitutes a lower quality part than the one specified. We could have wiring problems. We could have a misaligned voice coil that is not centered. We could have problems with the voice coil leads, these floating items connecting the voice coil to the connection terminal. We could have bad glue joints and potentially so-called crap in the gap. The measurements we can perform are on the right. By no means is this a complete list, and the measurements are just possibilities. A poorly magnetized motor can affect the speaker's sensitivity and impedance. Inconsistent materials could affect frequency response. For example, using a cheaper spider or thinner diaphragm could change the desired response. Obviously, if we wire incorrectly, this could affect the polarity. If we don't center the voice coil correctly in the magnetic gap, we could encounter problems with resonances and distortion. Voice coil leads could show up as rub and buzz. If the voice coil leads start hitting the cone or something else, that would sound bad and look like rub and buzz distortion. Bad glue joints would also look like rub and buzz distortion. Lastly, if debris falls into the gap, that would look like transients. I didn't talk much about transients, but SoundCheck has a loose particle detection algorithm for detecting transient distortion. This is non-harmonic based distortion. At this point, I'd like to turn the seminar over to Anastasia. She'll talk about these measurements in further detail and demonstrate measuring a loudspeaker with SoundCheck's installed Loudspeaker Complete Test sequence.
Thanks, Les. Anastasia here on the West Coast. And for this portion of our presentation, I'd like to demonstrate characterizing a loudspeaker using SoundCheck. We will have a simple setup with SoundCheck as the analyzer, the AmpConnect ISC as the test interface, and the SCM3 as our reference microphone.
The AmpConnect ISC is Listen's all-in-one test interface and is ideal for this loudspeaker test. It will function as the audio interface, power amplifier, impedance box, and microphone power supply as our test hardware, effectively replacing the individual components in the test diagram Les shared earlier. It comes fully calibrated from Listen, and the single interface eliminates potential cabling errors and is also more cost-effective. Looking at the setup close, AmpConnect connects to the PC with a single USB cable. Then the SCM3 measurement microphone is connected to the AmpConnect input, and the device under test speaker is connected to the AmpConnect's amplifier output.
In this configuration, all the signal paths except for the loudspeaker under test being measured are fully calibrated. We include many pre-written sequences with the SoundCheck installation, and today we will take a look at the complete test with AmpConnect from the loudspeaker sequences folder. It is a basic yet comprehensive test for measuring some of the speaker defects we've discussed thus far. While designed for end-of-line production testing, the sequence is also suitable for basic R&D testing. I'd like to mention that today's example at my home office is far from anechoic, and the results are only intended for demonstrative purposes. Firstly, we will check the hardware settings in the Setup menu. Under the Audio tab, our inputs and outputs are automatically assigned with an AmpConnect ISC, and the calibrations, settings, and VP values are auto-populated from the device, making setup a real breeze. AmpConnect ISC and other Listen hardware are true plug-and-play devices, providing full software control and auto-configuration through SoundCheck. Here, I've set the reference input bias to SCM voltage with 0 dB gain and routed channel 2 to Z low. I will use this input channel to measure impedance. Lastly, I've set the amplifier output A on, where I have connected the loudspeaker under test. Proper calibration of our audio hardware and signal I/O is key for sound results. Default signal paths have been automatically added in the installation for a quicker setup. The reference mic signal path is looking at input 1, reference channel of the AmpConnect, with the SCM calibration data file. The amp channel 1 output signal is using output 1 on the AmpConnect with reference to the AmpConnect calibration DAT file. Now let's take a closer look at the complete test sequence. We will evaluate a small loudspeaker. Starting with the stimulus, a step sign sweep or sweep stimulus will provide the most reliable excitation as it is relatively immune to background noise, and with harmonic track analysis allows us to analyze the fundamental and harmonics in parallel, which will return the frequency response and distortion with a single stimulus. This sequence also uses a compound stimulus combining two different step sweeps where the high frequency sweeps from 20K to 300 Hz at 12th octave resolution and 250 Hz to 50 Hz at a 3rd octave resolution. With typically smoother loudspeaker response at low frequencies, we can use that lower resolution and still achieve high accuracy and shorter test times. Once the stimulus is defined, we move on to the acquisition step. Here, the stimulus is played to the speaker under test, and the response is recorded simultaneously from the reference mic and impedance inputs. It's important to note here that SoundCheck can easily acquire an acoustic and electric audio signal simultaneously. With supported hardware, auto-rendering may be available on the input, where SoundCheck will automatically adjust the input gain of the signal path to optimize signal-to-noise ratio. Next, let's take a look at some of the most critical measurements and a couple slides to overview those. As Les briefly reviewed earlier, there are several critical measurements we are most interested in when testing a speaker. Frequency response, often referred to as the fundamental, is the response level of a DUT over the testing frequency range in dB. Ideally, we would like to see a completely flat curve here, but the perfect speaker doesn't exist. So we'll opt for minimized peaks and valleys within plus or minus 3 dB. This is the most concise indicator of a properly working speaker that does not present major resonances or reflections. Sensitivity is measured over the sound pressure response level per volt or output over input, and is important to confirm the linearity of the device. It also reveals a lot about the electronics of the speaker and ensures proper motor magnetization and level matching with other components like left and right drivers of earbuds. It can be considered over a single frequency, an average of several frequencies, or an entire bandpass range. Phase and polarity measurements would indicate any mismatch in electrical leads. And when wired properly, a positive input signal will cause the speaker to move outward as expected. The impedance measurement is another electrical characteristic over the frequency range of the response, and ideally presents a single peak to indicate the speaker resonance frequency, or F0. Additionally, we can calculate the Thiel small parameters. The last, and perhaps the most prominent measurement appropriate in all audio testing applications, is distortion. Most engineers might have you consider that less distortion is better. But it turns out that not all distortion is audible, or even sounds bad. And Steve Temmie will explain this concept in another seminar. When considering total harmonic distortion, it's typical to see higher percentages at lower frequencies. And that's due to greater cone displacement as the voice coil moves outside the linear range of the magnetic motor. Now that we've explored the critical measurements from a theoretical standpoint, let's take a look at how they're implemented in our sequence. Step number 4, analysis, compares the original stimulus to the acquired response and performs some type of analysis. We see at the distortion tab that the first through third harmonics will calculate the frequency response and THD percentage curves, whereas the 10th through 15 harmonic will calculate the rub and buzz percentage curve. The curves tab here summarizes which of these will be saved to the memory list to potentially be displayed at the end of the sequence. A second analysis step evaluates our impedance. The next few steps fall into the post-processing category of SoundCheck sequence functions and provide comparable values and results. Post-processing step number 6 calculates the sensitivity of the loudspeaker by averaging the y-axis response values across the entire frequency range of the sweep and returns a single average sensitivity value. We can easily modify this step to instead search over a few frequencies or an entire bandpass range as mentioned earlier. This sequence also contains pass-fail limits for average sensitivity, polarity, response, THD, and rub and buzz margins, and also impedance in steps number 7 through 17.
These limits are set arbitrarily, but can be edited to conform to your own pass-fail tolerances, referencing a golden curve or unit under test. In some cases, a fail limit may indicate an obvious problem. For example, failing polarity may suggest a potential wiring issue from our list of critical measurements. Let's run the sequence now. The final display step has been set up to show our curves and results cached to the memory list automatically at every completed step above, and it overwrites the graphs at every run of the sequence. Here is the frequency response and impedance on a graph with two separate axes. Here we have the distortion and a table of the pass and fail results. That mostly sums up the sequence, but it can be used as a baseline for customizing your own. Modify the sequence to meet your testing needs, whether by changing the limits, adding or removing analyses, and much more. Here is one example to save data to an external program. Click and drag the appropriate auto-save step from the step template guide. Select Data and choose the destination. Click Apply to complete the step.
That does it for our complete test sequence, where we explored the most common measurements of a loudspeaker. Thanks for your attention. Back to you, Les.
This concludes our presentation today. Thank you again to S&V Sanford for all your hard work organizing this event. Thank you for attending. We look forward to seeing you at our next event.